This is Group 2's final group project for EDEV 710.
This is Caitlin Meadows Cochran for EDEV 710, and in this section of our video, we're going to be discussing the sign test. The sign test is one of the non-parametric tests that we use in statistics to test the value of a hypothesized median for a sample of data. So we use either the single sample or the paired sample sign test to evaluate the value for a median that we've hypothesized based on a sample of data. To use the sign test, the first thing that you're going to do is hypothesize that value for your median. You're going to look at your population, look at the question to be answered, and hypothesize your value for the median in that population. At that point, you will then select a sample of data from the population to use in your sign test. You take each value from this sample of data and compare each value to your hypothesized median. Any value that falls above the hypothesized median on a number scale is assigned a plus or a positive sign. Any value that falls below a hypothesized median on the number scale is assigned a minus or a negative sign. And for those values that are the same as the hypothesized median for your sample of data, you assign a 0 value. Once you've given a sign or a 0 value to each piece of your sample, to each piece of data for your sample, you're going to compare the number of plus and minus signs that you have throughout your sample. And based on the number of positive and negative or plus and minus signs that you've got from your sample of data, you're going to determine what your test value is by comparing your positive and your negative column or category in your sample of data. Whichever category is smaller, that value is going to be used as the test value for your sign test. So, for example, if we have this sample of data and we have hypothesized that our median for this sample is 8, we're going to go through our sample and assign each value a plus or a minus sign based on where it falls in the number line in comparison to the number 8. So, for example, the number 10 will be assigned a positive sign. The number -7 will be assigned a negative sign, and so on and so forth throughout the sample of data. At that point, once we've assigned a positive or a negative sign to each value, we will need to compare how many numbers in this sample were assigned a positive value and how many numbers were assigned a negative value. And if you count, you see that 6 of our data values in our sample were assigned a positive sign or a plus sign, and 4 of our values were assigned a negative sign or a minus sign. So, based on the sign test, we'll use the smaller of these two numbers, which is 4, as our test value. Once you've determined your test value, then you have to decide your critical value for your sample. And for our purposes in this course, we'll use Table J, which is in Appendix C in the textbook, as our table of critical values. So once you've determined your test value and you've determined your critical value, you have to decide whether or not your null hypothesis is accepted or rejected based on the data that you were given. And so for the specific alpha value or for the specific significance in question, your null hypothesis is going to be rejected if the test value that you have found for your sample is less than or equal to your critical value. So here's your procedure, a little bit simpler. The first thing you've got to do is state your hypothesis and identify your claim for the median of your population. Then you find your critical value, compute your test value, and compare these two numbers to make the decision about your null hypothesis, whether you're going to reject your null hypothesis or accept your null hypothesis. And then take all this information and summarize it into the results statement for your research question. So here's an example. Suppose that we have a data set with 24 different observations. So your N value is going to be equal to 24. What we want to determine is if at a significance level of 0.05, is 33 a good estimate of the median for this population? So our null hypothesis is that our median is equal to 33. So based on the procedure for our sign test, the first thing that we're going to do is go through our data and assign each value a plus or a minus symbol or that 0 value based on where each number falls in relation to 33 on a number scale. So I've gone through and done that in the table, and you see that we have 18 data points that were assigned a minus value, 5 data points that were assigned a plus value, and we did have 1 data point of 33, which is equal to our hypothesized median, so we assigned it a 0 value. Based on this information, we determined that our test value for this problem is 5. And based on Table J in the appendix of the textbook, we decide that the critical value for this sample of data will be 6. So when we compare these numbers, we see that for this data set, our test value is less than our critical value. Therefore, we're going to reject our null hypothesis and say that at this significance level, our median is not going to be equal to 33. Now, up until this point, we've looked at this sign test in terms of single samples. But we can also perform what's called a paired sample sign test. And in a paired sample test, we've got 2 different dependent samples of data that are taken from the same population. Typically in statistics, we call these paired sample tests before and after tests because we're looking at some effect before and after an event or a circumstance in this population. Now, for a paired sample sign test, we're still going to assign each pair of values a positive or a negative sign, but we're going to determine that sign a little bit differently. We're going to subtract an after value from the before value for each data pair in the sample to determine what symbol they receive, positive or negative. So here's an example. A statistics professor is investigating the relationship between midterm exam score and final exam score. We've got 8 students and their scores on both exams. What we're trying to determine is at our specific level of significance, which is going to be 0.10 for this problem, is there enough evidence to decide if there's a difference in midterm and final exam scores? So the first thing we do is we determine our null hypothesis. And our null hypothesis is that student grades are not different from the midterm exam to the final exam. So here you see the same data table with the same information. I've just added a row across the bottom to show you the sign for each pair of data. So for example, for student number 1, we have 75 minus 82. We subtract the after from the before, and that would give us a negative result. So our sign for that data pair is going to be a negative. We do that for each column. We do that for each pair of data in our table, and you see the result of positives and negatives. When we compare, you see that we've got 5 negative pairs of data and we have 3 positive pairs of data. So our test value for this sample is going to be 3. Again, we refer back to Table J in that appendix, and we find that for an N equals 8 population at this significance level, our critical value is equal to 1. So now we compare our test value and our critical value to decide about our null hypothesis. In this case, our test value is greater than the critical value. 3 is greater than 1. So our null hypothesis cannot be rejected. There is not enough evidence based on the data in this sample to support the claim that students' midterm grades are different from their final exam grades. In this sample, we don't have enough information to decide if how students are scoring on their midterm exam really is different from how they score on their final exam. So hopefully through this section you have learned a little bit about the single sample and the paired sample sign test in statistics.
Hi, I'm Sonia, and I'll be discussing with you the Wilcoxon tests. The Wilcoxon tests are non-parametric tests that are used to compare distributions. The Wilcoxon rank sum test is used for independent samples, and the Wilcoxon sign rank test is used for dependent samples. They do not require the condition of normality. These tests are equivalent to the parametric tests Z and T for independent samples and the t-test for dependent samples. In the Wilcoxon test, the values of the data for both samples are combined and then ranked. When the values in each sample are summed and they are approximately the same, the null hypothesis is true. If there is a difference in the sums, the null hypothesis is greater than or equal to 10. Let's take a look. I have 2 independent samples of the SAT scores of juniors and seniors of a local high school. I will use the Wilcoxon rank sum test to see if there's a difference in the scores of the students at the 0.05 level of significance. I will use the z-scores of positive 1.96 and negative 1.96. Null hypothesis is that there is no difference in the scores of juniors and seniors at the high school. The alternative hypothesis and claim is that there is a difference in the scores of juniors and seniors at the high school. I'm going to be using the data. We have the scores here listed, as well as the classification. And under the classification, we have the value 1 listed for senior and the value 2 listed for the juniors. Go to Analyze, down to Non-Parametric Tests, over to Legacy Dialogues, over once more and click on 2 independent samples. 2 independent samples. Okay, and now as you can see here, our 2 independent samples will be our scores and classification. Our test variable list will be our scores, and we'll click on scores within classification. Our test variable list will be our scores, and we'll click on scores, which is already highlighted, and click here. And then classification will be our grouping variable. And as you can see, I have to go in and define the groups. And group 1 will be 1 for senior and 2 for the juniors. Click continue. And I will go in under options and click on descriptive. I also would like the exact method. And then I'll click OK. And Man Whitney U is already the test type that is highlighted, that is already marked. Negative 0.418. Negative 0.418. And it is, since it is a negative 0.418, which is greater than negative 1.96, we do not reject the null hypothesis. And therefore, we can conclude that there is no difference between the junior and senior SAT scores. There is not enough evidence to support the hypothesis that there is a difference between the two scores, the two set of scores. So we will, once again, we do not reject the null hypothesis, and we conclude that there is no different value. The Z value is negative 2.156. Negative 2.156. Now our critical value was 8. So that's a huge difference. And it's definitely less than 8, a negative 2.15. Therefore, we can conclude that we can reject the null hypothesis in this case. In this case, we will reject the null hypothesis that there is no difference, because there is a difference, and there's a significant difference between the post-test and the pre-test data. And click on, this time, 2 related samples. 2 related samples. Okay, and we have here the test pairs, which would be the pre-test, and we would click and it'll go over here, and we'll have the post-test, which will be variable 2. The Wilcoxon is already marked, is already checked for the test type. I'll go in statistics, and I already have the descriptives. Continue, and then press OK. And if as you see here, we have the pre-test listed, the pre-test data listed, the pre-test scores, and then we also have the post-test scores listed. And what we're going to do now, we're going to go to Analyze, move down to Non-Parametric Tests, Legacy Dialog, and click on, this time, 2 related samples. 2 related samples. Okay, and we have here the test pairs, which would be the pre-test and senior SAT scores. Now, let's look at the Wilcoxon sign rank test. When the samples are dependent, as they would be in a before and after test using the same subjects, the Wilcoxon signed rank test can be used in place of the t-test for dependent samples. Let's look at an example. A teacher was curious about the effectiveness of using arts integration in her classroom. She gave her students a pre-test on a specific topic in social studies. After implementing arts integration to her lesson, okay, and Man Whitney U is already the test type that is highlighted, that is already marked. Let's see here. Let's look at the output information. I'm most interested in my Z value because that's going to let me know whether or not the hypothesis is true or whether or not we should reject or do not reject the null hypothesis. And as you can see here, the Z value is listed as negative 0.418. Negative 0.418, and it is since.
I'm Nikki Bray, and we're going to talk about the Kruskal-Wallis test in statistics, Chapter 13, Section 5. The Kruskal-Wallis test is also called the H-test. It can be used to compare 3 or more means. Each sample size has to be greater than 5. With the Kruskal-Wallis test, use the chi-squared distribution to find the critical value, and the formula for the degrees of freedom to look up the critical value in the chi-squared distribution table is k minus 1, and k equals the number of groups. Now that we've went over some basics, we're going to work through an example to help you better understand the Kruskal-Wallis process. In this particular example that I've made up, and there's no research or no real values here, I've just come up with them on my own. An RD wants to find out if there's a difference in the diabetic patient's blood glucose if the patient receives exercise throughout the week. Is there a difference in blood glucose readings at alpha equals 0.05? And here we have the 3 different groups, A, B, and C. A received no exercise throughout the week. B received 15 minutes 3 times weekly of exercise, and C received 60 minutes 3 times weekly of exercise. And here you see the blood glucose readings. So for the solution, first we have to state the hypothesis and identify the claim. The null hypothesis is there is no difference in the patient's blood glucose readings depending on the amount of exercise they receive throughout the week. The alternative hypothesis is there is a difference in the patient's glucose readings depending on the amount of exercise they receive throughout the week. The next step to a Kruskal-Wallis problem is we have to identify the critical value. And the equation for the critical value is k minus 1 gives you the degrees of freedom. And k in this instance in the Kruskal-Wallis test is the number of groups. So 3 minus 3 was the number of groups because we had groups A, B, and C minus 1 equals 2 degrees of freedom. The critical value using table G, or the chi-squared table, is 5.991. Step 3. We have to compute the test value. The first step in computing the test value for a Kruskal-Wallis problem is you have to arrange the values from lowest to highest and rank them. So I went through here and I'll put all the values that we had in the problem, and I ranked them 1, 2, 3, 4, depending on where they fell and what group they were in. That's important in a Kruskal-Wallis test. And step B to compute the test values is find the sums of the ranks for each group. So A was ranked number 4, 6, 8, 13, and 15 for a total of 46. B was ranked 2, 5, 7, 12, and 14 for a total of 40. C was ranked 1, 3, 9, 10, and 11 for a total of 34. So for step C, in step 3 of finding the critical value, we have to substitute in for the formula to find the H critical value. So our sample size was 15, R1 was 46, that was the sum of rank 1, group A. R2 was the sum of was 40, was the sum of group 2, or group B, and R3 was the sum of group C, which was 34. And then N was equal for all the groups, was 5. So after we plug in the values and use the order of operations, we come up with a critical value of H equals 0.72. So now it's decision time. Since 0.72 is less than the critical value of 5.991, the decision is to not reject the null hypothesis. So now, after we have decided whether to reject or not, we've made our decision, and we have come to the conclusion and the summary that there is not enough evidence to reject the claim that there is no difference in the blood glucose readings of patients depending on the amount of exercise they receive throughout the week. The differences are not significant at alpha equals 0.05. And this concludes an example and a short lesson of the Kruskal-Wallis test.
Hello, I'm Kristen Zong, and I'll be presenting the Spearman Rank Correlation Coefficient in the RUNS test. You'll have to forgive my computer. It's kind of like a dinosaur, and it may sound a little loud. There's no additional fans blowing, it's just that loud. So please bear with me, and I hope you can still understand the information that I'm trying to present without being distracted by my loud dinosaur ancient computer. Alrighty. So the Spearman Correlation Coefficient test is a non-parametric test that measures the strength of the relationship between two ordinal variables. It measures the relationship between two variables that are also related, but they're not linear. Here's the formula for the calculation to determine the strength of the relationship of the data set. We will have an example later on in this presentation that will clearly delve into this calculation. The values can range from a positive one to a negative one. A positive one will be a perfect association. If there is a 0, there is no association between the ranks at all. If there is a negative one, it is a perfect negative association. So what does R mean after we have our calculation? Here is kind of a grouping of what each R can mean. You will have a grouping of either very strong, strong, moderate, weak, or very weak. Obviously, if you're trying to find a strong relationship between the data set, you want an R value of 0.8 to 1, or as close to it as you can. When we are plotting our data set, we will get graphs, and they'll be depicted in a monotonic relationship. A monotonic relationship, it's an important assumption of the Spearman rank correlation test. it is important to recognize that these relationships are less restrictive than a linear relationship. So as you see in the first two graphs, the first graph is more linear and the second graph is not as linear, but it still has kind of a linear flow. The far right graph is that non-monotonic graph. Later on in this presentation, we will see a graph that looks more so like the middle graph. There is still that positive relationship, even though it's not a perfect linear relationship, because that's not what this non-parametric test is depicting. It's not depicting a linear relationship, it's depicting the relationships between the data. With these graphs, we'll see as one value increases, so does the other value. And you can also see that one value may increase and the other value may decrease, and that's how you get the shape of these values. So here's our example. We have not used this example this semester. It was found online, and we wanted to determine the relationship of test scores between the 6th grade English and math class. So you first must state the hypothesis. The hypothesis is that there is no association between the English and math scores. Our alternate hypothesis is that there is an association between English and math scores. So here's our data set. I know that might be a little hard to see, so I will zoom in a little bit. Just bear with me here for a second. We'll just pretend that these lovely 6th graders didn't study that well the night before this test, because these are kind of low scores. There are 10 data sets, and you should have an even data set for each group. So here's what we must first do is rank the scores. We have to rank each score separately. You place a 1 with the highest value, and the lowest score gets the highest rank. So here in our example, we have 10 scores, our 10 data sets. Our lowest test score will get the highest rank. So you see in English, that's this 6th grader scored a 45, so they will get the highest score of a rank of a 10. The student who scored the 80, which is the highest test score in this data set, will receive a rank of a 1. I hope you can see that there are 261 in this data set, and so we must take the average of the ranking of these two, which happen to fall in the 6 and 7 ranking. We have no idea which one is actually 6 and which one is actually 7, so you have to give them the average of the two. We do the same thing with the math scores. Our lowest test score is that 40, so it gets the rank of the highest score, a 10, and our highest test score is a 77, so it will get the lowest rank of a 1. I know it can kind of be confusing, but if you work through this data again, you will understand how you get the rankings. Step 3, we must find the differences of our ranks. So you can see here, with the first score, you have a rank of 9 for English and 4 for math. The difference will be a 5. You'll leave all the integers in a positive number, because in the next step we will square everything, and even if you were to square -3 times a -3, or multiply a -3 times a -3, you would still get a positive 9. So we're just going to go ahead and leave everything positive. The fourth step is to square our differences, which we did in this last column, and all we did again is just square the difference of the ranks. The fifth step is to find the sum of the squares. I'll go ahead and back out a little bit now so we can see the whole screen, even though there's not data below, but this way you can see the full screen. Here, all I did was just add up every integer that was in the squared data to get the sum of our squares. The sixth step is just to substitute the data into the formula. We use the difference in ranks, which was the sum of the difference in ranks. That gives us our 54. There were 10 test scores, so we plug our 10 into the number of data pairs, and then you finish calculating the formula. In this example, it turns out that our R is a 0.67. So now that we have that data, we want to know exactly what it means. So we'll go ahead and flip back to the previous slide of what does R mean. And you can find it within this grouping. And so we know that this is a strong relationship, a strong correlation between with this formula and with this data set. So since we know what our R value is, we need to interpret the data. So this shows that with an R value of 0.67, it shows a positive, moderate, strong relationship. The higher your grade in English, the higher your grade in math will be. So we will go ahead and reject the null hypothesis that there is no association between these, because in fact we show that there is a positive association between math and English scores. I also wanted to go ahead and run the SPSS system since we have used this semester, and I wanted to input our data from this example to see what this computer program would actually get and see if my math was correct with what the computer gave us. I will again go ahead and zoom in since these are kind of small numbers. There we go. You will see that the correlation coefficient between math and English is a 0.669. And again here for English and math, it is a 0.669. When we did our calculations, we got a 0.67, so that is definitely, if you rounded up that 0.669, that would round up to 0.67. So it seems that my math was correct. I also wanted to show the graph of the data. Let me zoom out again. And this is using the SPSS data. We will see that monotonic relationship. It kind of looks like that graph in the middle from the previous example. It definitely shows a positive relationship, and it's not a positive linear, but it is that monotonic flow. Next, I will talk about another non-parametric test. This is called the runs test. This helps us to determine if our data is truly random. So it's a succession of identical letters preceded or followed by a different letter or no letter at all, such as the beginning or end of the succession. This test allows statisticians to determine randomness of this non-parametric data. So I'll go ahead and provide an example. Again, this example has not been used this semester. This is one I created on my own. And the coin, I went ahead and to a coin flip. I flipped it 10 times to see if it was actually random. So we must state our null hypothesis, and that hypothesis is that the coin was flipped 10 times and randomly landed on either heads or tails. That is our claim. And then our alternate is that the null hypothesis is not true. So we want to see if our claim is true. So first we must determine the number of runs in each sequence. Again, I'd flip this coin 10 times, and the H is labeled. That will be relationship to the heads, and the T is for tails. So I got a heads, 2 tails, a head and a head, 3 tails in a row, a head, and then a tail. You then must determine the run sequence. And so you start out by just, you must stop whenever the sequence changes into a different label. So our first run was just a head. The run 2 is 2 tails. Run 3 is 2 heads. Run 4 is 3 tails. Run 5 is 1 head. And run 6 is 1 tail. So we have a total of 6 runs. Step 3, we must find the critical values, and this is kind of where I just went ahead and just had all of my data organized into one slide, so then I could further figure out this example of to determine if my null hypothesis is true or not. So there were 6 runs. I flipped the coin 10 times. The alpha is at 0.05. The coin landed on heads 4 times. Coin landed on tails 6 times, And to help determine those critical values, I'm going to look at Table M in my textbook. So once I flipped to Table M, I went ahead and labeled the 4 times the coin landed on heads as N1. So N1 will equal 4. And N2 is going to be 6, which is in relationship to the tails, since the coin landed on tails 6 times, and N2 will equal 6. I look at Table N and I find that my critical values are 2 and 9. So now I must make the decision. Since the number of runs is 6, which falls in between the critical values of 2 and 9, do not reject the null hypothesis, because there's not enough evidence to reject the hypothesis that the coin flip results randomly landed on heads and tails. So with this example, we find that the coin flipped was truly random. I hope this presentation has helped you further understand the Spearman rank correlation coefficient and the runs test. Thank you for your time.